SwayamPrabha. Digital India. Educated India.
Welcome. So we have now in the module 2, that is week 2 of this course. So the main objective of this course is for this week is to learn the weak form and the most one of the popular method, Rayleigh-Ridge method. So to start with, we will go through a bit of elements of calculus of variation, which is very important for learning finite element. So I will, in this lecture, I will briefly discuss few things, that is what is essentially a functional is and how we can obtain the Euler-Lagrange equation, and some problem maybe we'll discuss. So this we will also continue in the next lecture also. So to start with, so what we have learned is that functional. What is functional? That we first learn, right? The new term is functional. So this term, what is a functional? So we have learned what is function. So for instance, if you have learned what is fx is a function. So we also know one of the important aspects of it, how to find out the local minimum or local maximum of a functional by taking its first derivative as 0, and then whether its second derivative is greater than 0 or less than 0, depending on that function is minimum or maximum. So this condition generally is known as the extremum condition. So now we know almost everything about the function. So now what we will learn is what is functional. So loosely speaking, a functional is essentially function of function. Loosely speaking, a function is a functional is a function of function. Now, do we have some example of functional? Yes, let us see some example. For instance, we all know what is a simply supported beam and how it deflects from our basic mechanics knowledge. So let us see what is this. So we know what is the load and other thing of this. So this is a UDL. So say this is W per unit length, and this beam, how it bends, we all know. So this is a simply supported condition. Maybe this is a roller, this is a pin end and other things. Now if I tell you that what is the strain energy density of this beam, then all of you can find it out very easily. The strain energy of this density of this beam is something like this: 0 to L, say EI by 2 d2w by dx2 whole square dx. Now how we are coming from this? So if you remember very simple formula, that is strain energy density is integral of m square by 2 ei. Probably you have also learned this. So just I substituted m as d2w dx2 m by ei. So this is multiplied by ei. So this I have just substituted here, and then this is the strain energy density. Now similarly, the potential energy density also I can write the strain energy density minus the work done, external work done. Here the external work done is the UDL, that is acting on this beam towards downwards, and that is essentially 0 to L Q into W dx. W is the displacement, the vertical displacement, and this is the x axis, this is the y axis. We can take the displacement downwards as positive. So this is y axis. So now this, if you look carefully, that this strain energy density and this thing, the potential energy density, both of them are functions of W. Now W itself is a function of x, because W is, if you know the deflection profile of this beam, then it looks like simply this. If you have done it in your BTech, or it looks like simply this. So this is the, so W is dependent on the x variable. Now in addition to that, this potential energy actually dependent on the second derivative of the W as well as the W itself. Now this kind of functions, or this kind of function of functions, are known as functionals. So we can also give a classical example of calculus of variation, that is the brachistochrone problem. If you heard previously the brachistochrone problem, we will start with the brachistochrone problem, and then we will come back to the problem which is essentially important to us for the structural engineering. Now in the brachistochrone problem, let us see what is the statement of the problem. Suppose there are 2 points in the 2D space, 1 and 2, there are 2 points. Now there is a particle which is under free fall. Suppose the particle is on free fall, and then the particle is falling under the action of the gravity. So under the action of the gravity, so now obviously the gravitational acceleration is constant if we take, and then it is also, one important thing is that frictionless. So friction is also neglecting, frictionless. So what will be the path if I just put release this particle from point 1, say it is a point 1 and point 2. So some of you may think that it will just fall downwards in a straight line, or some of you may think like this. So for instance, it may be like this. Some of you may think that this is this may fall from here to here. Now now our objective is not to from point 1 to this point, but rather point 1 to this point. So this could be another path. So another path I can draw actually several paths from which it can come. So these 3 parts I have drawn. So suppose it can go from here to here, and then here, and then here, and then here. Now which of this path will be the path for which the time taken will be minimum? So that is our problem. So now the problem is which path will have the minimum time. So which path will take minimum time. So how should I find out? So now if you look carefully, that these paths are essentially suppose this is my optimal path. Okay. So what do you mean by optimal? The optimal means that it takes the minimum time. So now this path may not be, this path may not be, and other paths may not be. So now if I take the x-axis along this and y-axis downwards or upwards, whatever may be, then if this is from here to here, if I estimate the distance, then let us say this is the y distance. Now from the elementary mechanics formula, we know that the velocity will be velocity of the particle will be root over 2gy, right? If it travels, it has to travel from the v. Now then how should I calculate the time? The time calculation is from very simple. Suppose I have a point, if I choose this coordinate of this point is x1 and coordinate of this point is x2, then the time integral from x1 to x2 is simply ds by v, right? Now this, what is ds? ds is the arc. Say simple arc, we know that is ds. Now this ds can also be written in this form. So that is dx square plus dy square. So these are differential element. So 1 by 2. Now let us say this is I, okay, the time. So this functional I we have to minimize such that it will take the minimum time. So our objective is to find out this yx. Now if I just simplify this, for instance, if I substitute dx squared, so I can take dx common and then write it in this way, that is root over 2gy, and then I can write it in this right. So dy, so just a second, so this will be whole square, so this will be whole square to the power half, and then I take dx out. So this is, if I take my dx as dy dx as y prime, then this functional looks like this. So 1 plus y prime square to the power half, and 2gy, this is also to the power half. So this is the functional that we need to minimize for solving this problem. So the objective here is to find out what will be the optimal path or yx. I will not go into the detail of this problem, rather to explain you what is the idea behind this calculus of variation. So essentially we are looking for functionals or the functions which are basically of this form, that is I integral from x1 to x2, x1 to x2, f of x, y and y prime. So this integral expression, this is a function of functions or functional, right? Now these functionals, if you look or if you study in detail, that you will see that this type of functional arises in different branches of physics, including mechanics. So now how to minimize or how to extremize this functional, that is our main goal, because to find out the optimal path of this Brachistochrone problem, we have to extremize the functional I here to get the y. Now suppose in this Brachistochrone problem, these paths, suppose I take the yx as my optimal path. Suppose let us take the optimal path, right? And the variation of yx, okay, the variation of yx can be any function, right? So this function can be this. So the variation can be this line also, this line also, or any other line also. So let us take these functions or these paths as y tilde x, right? Now this y tilde x is the approximate path, right? Let us take the approximate path as y tilde is as the approximate path. Now how should I write y tilde? So let us write y tilde in this form, that y tilde of x is the optimal path plus some another function which is eta x, right? Now this eta x, if you look carefully, this eta x cannot be arbitrary. Why it cannot be arbitrary? Because eta x has to follow some condition. What are those conditions here? The conditions here that the body or the particle must start from here and must reach here. So that is my condition. So naturally at these two positions, the values of y we know, or basically we know y at x1 and y at, suppose this is y1, and y at x2 we know, which is y2. Now both of these things we know. So naturally at these 2 points eta x1, that is eta of x1 has to be 0 and eta of x2 has to be 0. So both of these has to be 0. So eta x will be such that this condition has to be fulfilled. This is called the admissibility criteria or the admissible function. Now our objective is to find out these y tilde as y. So what will be the optimal path? So to do that, we need to do the minimization, obviously, and so to convert this functional minimization to a scalar minimization, let us multiply with a small epsilon. So this small epsilon, or the scalar quantity epsilon. So now I can write my functional y as I tilde, because I don't know the functional y or function y. So I can write my this functional as integral of x1 to x2 f of x y tilde dash. So this is my now approximate functional. Now if I just expand it a little bit, so this is x y plus eta y, eta right, and then y prime plus eta into epsilon into eta prime. So this is my functional. Now, how to minimize this I tilde in such a way that we get y? So, if you look carefully that this condition, the approximation of this y tilde or the y is such that if I just put epsilon equals to 0, I can get the optimal function. So, naturally, in this functional, I convert, if I write it in this way, that this is a function of epsilon only, then epsilon at equal to 0 is the optimal path. So, this is evident from this approximation. So, essentially what I mean by that, the d I tilde by d epsilon, if I take and if I do it at epsilon equals to 0, then then this has to be 0 for I tilde to be optimal, I tilde to be optimal. Now that optimal that I tilde will give my optimal path yx. So this is the basics of this. I can express it in terms of Taylor series, and then simply by writing or the expressing this I tilde in terms of, suppose if I write this I tilde and expressed it in terms of around epsilon equals to 0. So, I at epsilon equals to 0, then d. So, I tilde at epsilon equals to 0, d I tilde by d epsilon at epsilon equals to 0 into epsilon plus d2 I tilde d epsilon 2 at epsilon equals to 0 into epsilon square by factorial 2, and so on, the other higher order terms. So, naturally the first order criteria or the extremization criteria which we follow from the function minimization or the function optimization, that is that I tilde I tilde at epsilon equals to 0 minus, this is I tilde at epsilon equals to 0 is nothing but I. So, essentially this has to be d I tilde by d epsilon equals to 0 and the other terms. So, this quantity is known as the variation of the functional I. Now we will come to that. So how to do that first? Let us see how we can do that. So suppose this is I tilde. We know I tilde now. That is our I tilde is integral of x1 to x2 f of x comma y plus eta epsilon eta comma y prime plus epsilon eta prime, right? We know that. So this is my I tilde. Now d I tilde by d epsilon, if I had to compute, then it is just a chain rule I will follow, because the following the chain rule is it is just simply the chain rule. So what is that? So del f by del y into del dy by d epsilon plus df by, so I am writing partial for f. If you look carefully, that I am writing partial for f y prime into dy prime by d epsilon. So this is my derivative formula, derivatives. Now I know all these values because I know the y tilde and other things. So I know all these values, what are those, what are those. So these are I can just do it in terms of tilde also, because I have not used yet the epsilon as yet 0. So if I just use epsilon equals to 0, so these can be your y prime. So naturally I can just write x1 to x2, so del f by del y tilde, or del y tilde by del epsilon is nothing but your eta, and then del f by del y tilde is your eta dash, right? So this is we know from this expression that y tilde is essentially y plus epsilon into eta. Now if I just invoke now the condition that d I tilde by d epsilon, if I just take epsilon equals to 0, so I can write it this in terms of I can write these things in terms of epsilon. So this is my x1, this is my x2. So this is my x2. So now this del f by del y tilde, I can write it as del f by del y into eta plus del f by del y prime, eta prime, right? So this is very simple for me. Now if I had to expand this, for instance, if I had to expand this, so this is nothing but integral of x1 to x2. I write del f by del y eta plus, now this I can do the integration by parts. So if I want to convert these things, so let us not write this here. So let me write it in this way, that del f by del y into eta plus this quantity I can write it in the I can do separately the integration and parts, integration by parts, and then convert this thing to a eta or the transfer the eta thing. So if I do the integration by parts, then what I will have is just plus, so del f by del y prime. So this will be eta, so this will be at x equals to x1 to x equals to x2. Now then again I will have this quantity, this dd, so integration of in x1 to x2 will be, so then this will be ddx of del f y prime into eta x and dx. So this is what we can see this. So if you look carefully that this eta x this eta x we know at x1 and x2 and which is 0 essentially. So for the problem that we discussed, the Brachistochrone problem. Now this is why I wanted to discuss Brachistochrone problem, because this is very simple to understand. Now this, if I just write it these two terms together, then what I will get is del f by del x or del y minus d dx of del f by del y prime into eta x. So I am writing eta as a function of x here, and then I am just writing that the boundary term, that is due to the integration by parts. So so this is the thing. Now if you look for the from the Brachistochrone problem aspect, then this quantity goes to 0, right? So this quantity, I can just simply say that this quantity can simply be 0. So this quantity will be the only quantity I need to preserve, right? Now the minimization condition or the extremization condition that we have found out is that di tilde d epsilon must be at epsilon equals to 0, must be equals to 0. So naturally this quantity will be my 0, right? Now look carefully that making this quantity 0 is essentially making this quantity 0, because eta x is any admissible arbitrary function. So naturally I will say that del f by del y minus d dx of del f by del y prime equals to 0. So this is my condition. Now this is for any eta x. So obviously eta x has to be admissible. The meaning of this admissibility means that eta x has to satisfy the boundary conditions, or specifically the in case of Brachistochrone problem, that at point x1 and point x2 it has to be 0. So this is known as the Euler-Lagrange equation. Euler-Lagrange equation of the functional, or the Euler-Lagrange equation. So now so I stop here. So we learned how we can find out the Euler-Lagrange equation of a functional if it is given in a general form. So I start with a very general form, which is this, right? And then I derive the condition, which is essentially this condition. So this condition means that this is your this has to be the minimization condition or the extremization, specifically the extremization condition. Now this extremization condition leads to this equation has to be 0. So this condition leads to this condition has to be 0. So this is known as the Euler-Lagrange equation. We will see its application in the next lecture. Thank you.